Jyoti of class MSc Chemistry first year is here to read out a chapter from class 11th NCERT, and this is unit 10, and the name of chapter is the S block elements. The first element of alkali and alkaline earth metals differ in many respects from the other members of the group. The S block elements of the periodic table are those in which the last electron enters the outermost s orbital. As the s orbital can accommodate only two electrons, two groups 1 and 2 belong to the S block of the periodic table. Group 1 of the periodic table consists of the elements lithium, sodium, potassium, rubidium, cesium and francium. They are collectively known as the alkali metals. These are so called because they form hydroxides on reaction with water, which are strongly alkaline in nature. The elements of group 2 include beryllium, magnesium, calcium, strontium, barium and radium. These elements, with the exception of beryllium, are commonly known as alkaline earth metals. These are so called because their oxides and hydroxides are alkaline in nature, and these metal oxides are found in the earth's crust. Among the alkali metals, sodium and potassium are abundant, and lithium, rubidium and cesium have much lower abundance. Francium is highly radioactive. Its longest lived isotope, francium 223, has a half-life of only 21 minutes. Of the alkaline earth metals, calcium and magnesium rank 5th and 6th in abundance respectively in the earth's crust. Strontium and barium have much lower abundance. Beryllium is rare and radium is the rarest of all, comprising only 10 to the power minus 10% of igneous rocks. The general electronic configuration of S block elements is noble gas NS1 for alkali metals and noble gas NS2 for alkaline earth metals. Next, lithium and beryllium, the first elements of group 1 and group 2 respectively, exhibit some properties which are different from those of the other members of the respective group. In these anomalous properties, they resemble the second element of the following group. Thus, lithium shows similarities to magnesium and beryllium to aluminium in many of their properties. This type of diagonal similarity is commonly referred to as diagonal relationship in the periodic table. The diagonal relationship is due to the similarity in ionic sizes or charge divided by radius ratio of the elements. Monovalent sodium and potassium ions and divalent magnesium and calcium ions are found in large proportions in biological fluids. These ions perform important biological functions such as maintenance of ion balance and nerve impulse conduction. Next topic, we have group 1 elements, alkali metals. The alkali metals show regular trend in their physical and chemical properties with the increasing atomic number. The atomic, physical and chemical properties of the alkali metals are discussed below. Next is electronic configuration. All the alkali metals have one valence electron NS1 outside the noble gas core. The loosely held S electron in the outermost valence shell of these elements make them the most electropositive metals. They readily lose electron to give monovalent M positive ions, hence they are never found in free state in nature. If we talk about lithium, its electronic configuration is 1s2 2s1. Sodium symbol is Na, lithium symbol was Li, and sodium electronic configuration is 1s2 2s2 2p6 3s1. Potassium symbol is K, electronic configuration is 1s2 2s2 2p6 3s2 3p6 4s1. Rubidium symbol is Rb, electronic configuration is 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 5s1. Cesium symbol is Cs, electronic configuration is 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 4d10 5s2 5p6 6s1, or we can write Xe 6s1. Next is francium, symbol is Fr, its electronic configuration is radon in bracket and 7s1. Next topic is atomic and ionic radii. The alkali metal atoms have the largest sizes in a particular period of the periodic table with increase in atomic number, the atom becomes larger. The monovalent ions M positive are smaller than the parent atom. The atomic and ionic radii of alkali metals increase on moving down the group, that is, they increase in size while going from lithium to cesium. Next topic is ionization enthalpy. The ionization enthalpies of the alkali metals are considerably low and decrease down the group from lithium to cesium. This is because the effect of increasing size outweighs the increasing nuclear charge, and the outermost electron is very well screened from the nuclear charge. Next topic is hydration enthalpy. The hydration enthalpies of the alkali metal ions decrease with increase in ionic sizes. Their order is Li positive, then decreasing, it is a decreasing order where Li positive, then we have Na positive, then potassium positive, rubidium positive and cesium positive ion. Lithium ion has maximum degree of hydration, and for this reason lithium salts are most commonly hydrated. Example LiCl.2H2O. Next topic is physical properties. All the alkali metals are silvery white, soft and light metals. Because of the large size, these elements have low density which increases down the group from lithium to cesium. However, potassium is lighter than sodium. The melting and boiling points of the alkali metals are low, indicating weak metallic bonding due to the presence of only a single valence electron in them. The alkali metals and their salts impart characteristic color to an oxidizing flame. This is because the heat from the flame excites the outermost orbital electron to a higher energy level. When the excited electron comes back to the ground state, there is emission of radiation in the visible region of the spectrum as given below. If we talk about metal lithium, then its color is crimson red. Its wavelength in nanometer is given as 670.8. Sodium, its color is yellow and its wavelength is given 589.2. Potassium color is violet, wavelength is 766.5. Rubidium color is red violet, wavelength is 780.0. Cesium color is blue and the wavelength is 455.5. Alkali metals can therefore be detected by the respective flame test and can be determined by the flame photometry or atomic absorption spectroscopy. These elements, when irradiated with light, the light energy absorbed may be sufficient to make an atom lose electron. Next, we are given with a table which represents the atomic and physical properties of the alkali metals. If we talk about lithium, its atomic number is 3, its atomic mass and unit is gram per mole, its atomic mass is 6.94, electronic configuration is helium 2s1, ionization enthalpy in kilojoule per mole is 520, hydration enthalpy in kilojoule per mole is minus 506, metallic radius in picometer is 152, ionic radius in picometer is 76, melting point in Kelvin is 454, boiling point in Kelvin is 1615, density in gram per centimeter cube is 0.53, standard potentials is minus 3.04, occurrence in lithosphere is 18. It's given as ppm parts per million. Okay, next if we talk about sodium, its atomic number is 11, atomic mass is 22.99, electronic configuration is neon 3s1, ionization enthalpy is 496 kilojoule per mole, hydration enthalpy is minus 406 kilojoule per mole, metallic radius in picometer is 186, ionic radius in picometer is 102, melting point is 371 in Kelvin, boiling point is 1156 in Kelvin, density in gram per centimeter cube is 0.97, standard potential is minus 2.714, occurrence in lithosphere is 2.27. Next we have potassium, atomic number 19, atomic mass 39.10, electronic configuration argon 4s1, ionization enthalpy 419, hydration enthalpy minus 330, metallic radius 227, ionic radius 138, melting point is 336, boiling point is 1032, density is 0.86, standard potential is minus 2.925, occurrence in lithosphere is 1.84. Next we have rubidium, atomic number 37, atomic mass 85.47, electronic configuration krypton 5s1, ionization enthalpy is 403, hydration enthalpy minus 310, metallic radius 248, ionic radius 152, melting point 312, boiling point 961, density is 1.53, standard potential is minus 2.930, occurrence in lithosphere is 78 to 12 picometer. Next is cesium, atomic number 55, atomic mass 132.91, electronic configuration xenon 6s1, ionization enthalpy 376, hydration enthalpy minus 276, metallic radius 265, ionic radius 167, melting point 302, boiling point 944, density 1.90, standard potential minus 2.927, occurrence in lithosphere is 2 to 6 picometer. Last is francium, atomic number is 87, atomic mass is 223, electronic configuration radon 7s1, ionization enthalpy is nearly equal to 375, and hydration enthalpy and metallic radius is particularly not given. Ionic radius is 180, and occurrence in lithosphere is 10 to the power minus 18 picometer. Okay, now next. This property makes cesium and potassium useful as electrodes in photoelectric cells. Next we have topic chemical properties. The alkali metals are highly reactive due to their large size and low ionization enthalpy. The reactivity of these metals increase down the group. First is reactivity towards air. The alkali metals tarnish in dry air due to the formation of their oxides, which in turn react with moisture to form hydroxides. They burn vigorously in oxygen forming oxides. Lithium forms monoxide, sodium forms peroxide. The other metals form superoxides. The superoxide O2 negative ion is stable only in the presence of large cations such as potassium, rubidium and cesium. A reaction is given where 4 lithium plus oxygen dioxygen reacts to give 2 Li2O, which is an oxide. Next we have 2 sodium plus dioxygen gives Na2O2, that is a peroxide. Whereas another reaction is metal plus O2 gives MO2, which is a superoxide, and this metal can be potassium, rubidium or cesium. In all these oxides, the oxidation state of the alkali metal is +1. Lithium shows exceptional behavior in reacting directly with nitrogen of air to form nitride Li3N as well. Because of their high reactivity towards air and water, alkali metals are normally kept in kerosene oil. Now next is given a question, what is the oxidation state of potassium in KO2? And its answer is the superoxide species is represented as O2 negative since the compound is neutral. Therefore, the oxidation state of potassium is +1. Next, second topic we have given reactivity towards water. The alkali metals react with water to form hydroxide and dihydrogen. Reaction is given 2 metal plus 2 H2O gives 2 M positive plus 2 OH negative plus H2, where M is an alkali metal. It may be noted that although lithium has most negative E negative value, its reaction with water is less vigorous than that of sodium, which has the least negative E negative value among the alkali metals. This behavior of lithium is attributed to its small size and very high hydration energy. Other metals of the group react explosively with water. They also react with proton donors such as alcohol gases, ammonia and alkynes. Third is reactivity towards dihydrogen. The alkali metals react with dihydrogen at about 673 Kelvin, lithium at 1073 Kelvin to form hydrides. All the alkali metals hydrides are ionic solids with high melting points. A reaction is given 2 metal plus H2 gives 2 M positive H negative. Next is reactivity towards halogen. The alkali metals readily react vigorously with halogens to form ionic halides M positive X negative. However, lithium halides are somewhat covalent. It is because of the high polarization capability of lithium ion, the distortion of the electron cloud of the anion by the cation is called polarization. The Li positive ion is very small in size and has high tendency to distort electron cloud around the negative halide ion. Since the anion with large size can be easily distorted among halides, lithium iodide is the most covalent in nature. Fifth is reducing nature. The alkali metals are strong reducing agents, lithium being the most and sodium the least powerful. The standard electrode potential, which measures a reducing power, represents the overall change. A reaction is given where a solid metal, if it gives gaseous metal, then it is sublimation enthalpy. If a gaseous metal gives a M positive and an electron is being removed, then it is a ionization enthalpy. If a gaseous metal, ionic gaseous metal plus water is added to it, then it gives M positive aqueous, which is hydration enthalpy. With the small size of its ion, lithium has the highest hydration enthalpy, which accounts for its high negative E negative value and its high reducing power. Next, again a question is given. The E negative for Cl2 slash Cl negative is plus 1.36. For I2 slash I negative is plus 0.53. For Ag positive slash Ag is 0 plus 0.79. For Na positive slash Na is minus 2.71, and for lithium positive by lithium is minus 3.04. Arrange the following ionic species in decreasing order of reducing strength, where I negative, Ag, Cl negative, Li and Na is given. So the answer is, the order is in the decreasing order, where lithium comes first, then sodium, then I negative, then Ag, then last Cl negative in a decreasing order. Sixth, we have solutions in liquid ammonia. The alkali metals dissolve in liquid ammonia, giving deep blue solutions which are conducting in nature. A reaction is given where M plus X plus Y in bracket ammonia gives M ammonia X ions plus E NH3 bracket Y negative ions. The blue color of the solution is due to the ammoniated electron, which absorbs energy in the visible region of light and thus imparts blue color to the solution. The solution are paramagnetic and on standing slowly liberate hydrogen, resulting in the formation of amide. Again a reaction is given where M positive Am, here Am denotes ammonia, plus electron plus ammonia liquid ammonia gives MnH2 ammonia plus half H2 hydrogen gas. In concentrated solution, the blue color changes to bronze color and becomes diamagnetic. Next topic is uses. Lithium metal is used to make useful alloys, for example with lead to make white metals, bearings for motor engines, with aluminium to make aircraft parts, with magnesium to make armor plates. It is used in thermonuclear reactions. Lithium is also used to make electrochemical cells. Sodium is used to make a sodium lead alloy needed to make PbEt4 and PbMe4. These organolead compounds were earlier used as anti-knock additives to petrol, but nowadays vehicles use lead-free petrol. Liquid sodium metal is used as a coolant in a fast breeder nuclear reactors. Potassium has a vital role in biological systems. Potassium chloride is used as a fertilizer. Potassium hydroxide is used in the manufacture of soft soap. It is also used as an excellent absorbent of carbon dioxide. Cesium is used in devising photoelectric cells. Next topic is general characteristics of the compounds of the alkali metals. All the common compounds of the alkali metals are generally ionic in nature. General characteristics of some of the compounds are discussed here. First is oxides and hydroxides. On combustion in excess of air, lithium forms mainly the oxide Li2O plus some peroxide Li2O2. Sodium forms the peroxide Na2O2 and some superoxide NaO2. Whilst potassium, rubidium and cesium form the superoxides MO2. Under appropriate conditions, pure compounds M2O, M2O2 and MO2 may be prepared. The increasing stability of the peroxide or superoxide as the size of the metal ion increases is due to the stabilization of large anions by larger cations through lattice energy effects. These oxides are easily hydrolyzed by water to form the hydroxides according to the following reactions. Reactions are given M2O plus H2O gives 2M positive plus 2OH negative ions. M2O2 plus 2H2O gives 2M positive ions plus 2OH negative ions and H2O2. Next is 2MO2 plus 2H2O gives 2M positive ions, 2OH negative ions plus H2O2 and plus dioxygen. The oxides and the peroxides are colorless when pure, but the superoxides are yellow or orange in color. The superoxides are also paramagnetic. Sodium peroxide is widely used as an oxidizing agent in inorganic chemistry. Next question is, why is KO2 paramagnetic? The superoxide O2 negative is paramagnetic because of one unpaired electron in pi star 2p molecular orbital. Next we have the hydroxides, which are obtained by the reaction of the oxides with water, are all white crystalline solids. The alkali metal hydroxides are the strongest of all bases and dissolve freely with water with the evolution of much heat on the account of intense hydration. Next topic is halides. The alkali metal halides MX, where halogen can be fluorine, chlorine, bromine, iodine, are all high melting colorless crystalline solids. They can be prepared by the reaction of appropriate oxides, hydroxide or carbonate with aqueous hydrohalic acid HX. All of these halides have high negative enthalpies of formation. The del F H negative values for fluorides become less negative as we go down the group, whilst the reverse is true for del F H negative for chlorides, bromides and iodides. For a given metal, del F H negative always becomes less negative from fluoride to iodide. The melting and boiling points always follow the trend fluoride. This is a decreasing order trend where fluoride, then chloride, then bromide and at last iodide. All these halides are soluble in water. The low solubility of LiF in water is due to its high lattice enthalpy, whereas the low solubility of CSI is due to smaller hydration enthalpy of its two ions. Other halides of lithium are soluble in ethanol, acetone and ethyl acetate. LiCl is soluble in pyridine also. Next topic is salts of oxoacids. Oxoacids are those in which the acidic proton is on a hydroxyl group with an oxo group attached to the same atom. Example, carbonic acid H2CO3, sulfuric acid H2SO4. The alkali metal forms salt with all the oxoacids. They are generally soluble in water. They are generally soluble in water and thermally stable. Their carbonates M2CO3 and in most cases the hydrogen carbonates MHCO3 are highly stable to heat. As the electropositive character increases down the group, the stability of the carbonates and hydrogen carbonates increases. Lithium carbonate is not so stable to heat. Lithium, being small in size, polarizes a large CO32 negative ion, leading to the formation of more stable Li2O and CO2. Its hydrogen carbonate does not exist as a solid. Next topic we have anomalous properties of lithium. The anomalous behavior of lithium is due to the first, exceptionally small size of its atom and ion. Second, high polarizing power, that is charge by radius ratio. As a result, there is an increased covalent character of lithium compounds which is responsible for their solubility in organic solvents. Further, lithium shows diagonal relationship to magnesium which has been discussed subsequently. Points of difference between lithium and other alkali metals. First, lithium is much harder. Its melting and boiling point are higher than the other alkali metals. Second, lithium is least reactive but the strongest reducing agent among all the alkali metals. On combustion in air, it forms mainly monoxide Li2O and the nitride Li3N, unlike other alkali metals. Third is lithium chloride is deliquescent and crystallizes as a hydrate LiCl2H2O, whereas other alkali metal chlorides do not form hydrates. Fourth is lithium hydrogen carbonate is not obtained in the solid form while all other elements form solid hydrogen carbonates. Fifth is lithium, unlike other alkali metal, forms no ethanide on reaction with ethine. Sixth, lithium nitrate when heated gives lithium oxide Li2O, whereas other alkali metals nitrates decompose to give the corresponding nitrite. Example, 4LiNO3 gives 2Li2O plus 4NO2 plus dioxygen. Other reaction is 2NaNO3 gives 2NaNO2 plus O2. Seventh is LiF and Li2O are comparatively much less soluble in water than the corresponding compounds of the other alkali metals. Next topic is points of similarities between lithium and magnesium. The similarity between lithium and magnesium is particularly striking and arises because of their similar sizes, atomic radii. Lithium's atomic radius is 152 picometer, magnesium is 160 picometer. Ionic radii, Li positive, its ionic radii is 76 picometer, and Mg2 positive, it's 72 picometer. The main points of similarities are: first, both lithium and magnesium are harder. Then second, we have harder and lighter than other elements in the respective group. Secondly, lithium and magnesium react slowly with water. Their oxides and hydroxides are much soluble than their hydroxide decomposes on heating. Both form a nitride Li3N and Mg3N2 by direct combination with nitrogen. Third point, the oxides Li2O and MgO do not combine with excess oxygen to give any superoxide. Fourth, the carbonates of lithium and magnesium decompose easily on heating to form the oxides and CO2. Solid hydrogen carbonates are not formed by lithium and magnesium. Fifth, both LiCl and MgCl2 are soluble in ethanol. Sixth, both LiCl and MgCl2 are deliquescent and crystallize form aqueous solution as hydrates LiCl.2H2 and MgCl2.8H2. Next topic is some important compounds of sodium. Industrially important compounds of sodium include sodium carbonate, sodium hydroxide, sodium chloride and sodium bicarbonate. The large scale production of these compounds and their uses are discussed below. First is sodium carbonate. Washing soda, its formula is Na2CO3.10H2. Sodium carbonate is generally prepared by the Solvay process. In this process, advantage is taken of the low solubility of sodium hydrogen carbonate, whereby it gets precipitated in the reaction of sodium chloride with ammonium hydrogen carbonate. The latter is prepared by passing CO2 to a concentrated solution of sodium chloride saturated with ammonia, where ammonium carbonate followed by ammonium hydrogen carbonate are formed. The equation for the complete process may be written as 2 ammonia plus water plus CO2 gives NH4 whole twice CO3. Next is NH4 whole twice CO3 plus water plus CO2 gives 2 NH4 HCO3. फिर next third reaction is NH4 HCO3 plus NaCl gives NH4Cl plus NaHCO3. Sodium hydrogen carbonate crystal separates. These are heated to give sodium carbonate. Then we have 2 NaHCO3 gives Na2CO3 plus CO2 plus H2. In this process, ammonia is recovered when the solution containing ammonium chloride is treated with calcium hydroxide. Calcium chloride is obtained as a byproduct. Then next reaction is 2 NH4Cl plus calcium hydroxide gives 2 ammonia moles plus calcium chloride plus water. It may be mentioned here that Solvay process cannot be extended to the manufacture of potassium carbonate because potassium hydrogen carbonate is too low soluble to be precipitated by the addition of ammonium hydrogen carbonate to a saturated solution of potassium chloride. Next is properties. Sodium carbonate is a white crystalline solid which exists as a decahydrate Na2CO3.10H2. This is also called washing soda. It is readily soluble in water. On heating, the decahydrate loses its water of crystallization to form monohydrate. Above 373 Kelvin, the monohydrate becomes completely anhydrous and changes to a white powder called soda ash. Reaction is Na2CO3.10H2 at 375 Kelvin gives Na2CO3.H2 plus 9H2. Next is Na2CO3.H2 more than 373 Kelvin gives Na2CO3 plus H2. Carbonate part of sodium carbonate gets hydrolyzed by water to form an alkaline solution. CO3 2 negative plus H2O gives HCO3 negative plus OH negative. Next is uses. Firstly, it is used in water softening, laundering and cleaning. Second, it is used in the manufacture of glass, soap, borax and caustic soda. Third, it is used in paper, paints and textile industries. Fourth, it is an important laboratory reagent both in qualitative and quantitative analysis. Next is sodium chloride NaCl. The most abundant source of sodium chloride is seawater, which contains 2.7 to 2.9% by mass of the salt. In tropical countries like India, common salt is generally obtained by the evaporation of seawater. Approximately 50 lakh tons of salt are produced annually in India by solar evaporation. Crude sodium chloride, generally obtained by crystallization of brine solution, contains sodium sulfate, calcium chloride and magnesium chloride as impurities. Calcium chloride CaCl2 and magnesium chloride MgCl2 are impurities because they are delicescent, absorb moisture easily from the atmosphere. To obtain pure sodium chloride, the crude salt is dissolved in minimum amount of water and filtered to remove insoluble impurities. The solution is then saturated with hydrogen chloride gas. Crystals of pure sodium chloride separate out. Calcium and magnesium chloride, being more soluble than sodium chloride, remains in the solution. Sodium chloride melts at 1081 Kelvin. It has a solubility of 36.0 gram in 100 gram of water at 273 Kelvin. The solubility does not increase appreciably with increase in temperature. Uses: firstly, it is used as a common salt or table salt for domestic purpose. Secondly, it is used for the preparation of Na2O2, NaOH and Na2CO3. Next, we have sodium hydroxide, caustic soda. Formula is NaOH. Sodium hydroxide is generally prepared commercially by the electrolysis of sodium chloride in Kellner cell. A brine solution is electrolyzed using a mercury cathode and a carbon anode. Sodium metals discharged at the cathode combines with mercury to form sodium amalgam. Chlorine gas is evolved at the anode. Cathode reaction is given Na positive gains the electron. Mercury gives Na amalgam. At anode, Cl negative gives half Cl2 plus electron is removed. The amalgam is treated with water to give sodium hydroxide and hydrogen gas. 2 Na amalgam plus 2 H2O gives 2 NaOH plus 2 Hg and H2 is removed. Sodium hydroxide is a white translucent solid. It melts at 591 Kelvin. It is readily soluble in water to give a strong alkaline solution. Crystals of sodium hydroxide in delicescent. The sodium hydroxide solution at the surface reacts with the CO2 in the atmosphere to form Na2CO3. Uses: it is used firstly in the manufacture of soap, paper, artificial silk and a number of chemicals. Secondly, in petroleum refining. Thirdly, in the purification of bauxite. Fourthly, in the textile industries for mercurizing cotton fabrics. Fifth, for the preparation of pure fats and oils. Sixth, as a laboratory reagent. Next, we have sodium hydrogen carbonate, baking soda, NaHCO3. Sodium hydrogen carbonate, baking soda. Formula NaHCO3. Sodium hydrogen carbonate is known as baking soda because it decomposes on heating to generate bubbles of carbon dioxide, leaving holes in cakes or pastries and making them light and fluffy. Sodium hydrogen carbonate is made by saturating a solution of sodium carbonate with carbon dioxide. The white crystalline powder of sodium hydrogen carbonate, being less soluble, gets separated out. Na2CO3 plus water plus CO2 gives 2 NaHCO3. Sodium hydrogen carbonate is a mild antiseptic for skin infections. It is used in fire extinguishers. Next topic is biological importance of sodium and potassium. A typical 70 kg man contains about 90 gram of sodium and 170 gram of potassium, compared with only 5 gram of iron and 0.06 gram of copper. Sodium ions are found primarily on outsides of cell, being located in blood plasma and the interstitial fluid which surrounds the cells. These ions participate in the transmission of nerve signals, in regulating the flow of water across cell membranes, and in the transport of sugars and amino acids into cells. Sodium and potassium, although so similar chemically, differ quantitatively in their ability to penetrate cell membranes, in their transport mechanisms, and in their efficiency to activate enzymes. Thus, potassium ions are the most abundant cations within cell fluids, where they activate many enzymes, participate in the oxidation of glucose to produce ATP, and with sodium are responsible for the transmission of nerve signals. There is a very considerable variation in the concentration of sodium and potassium ions found on the opposite sides of the cell membrane. As a typical example, in blood plasma, sodium is present to the extent of 143 meter mole per liter, whereas the potassium level is only 5 meter mole per liter within the red blood cells. These concentrations change to 10 meter mole per liter sodium ion and 105 meter mole per liter potassium ions. These ionic gradients demonstrated that a discriminatory mechanism called the sodium potassium pump operates across the cell membrane, which consumes more than one third of the ATP used by a resting animal and about 15 kg per 24 hour in a resting human. Next topic is group 2 elements, which are alkaline earth metals. The group 2 elements comprises beryllium, magnesium, calcium, strontium, barium and radium. They follow alkali metals in the periodic table. These except beryllium are known as alkaline earth metals. The first element, beryllium, differs from the rest of the members and shows diagonal relationship to aluminium. The atomic and physical properties of the alkaline earth metals are shown in table 10.2. Next, we have electronic configuration. These elements have 2 electrons in the s orbital of the valence shell. The general electronic configuration may be represented as noble gas NS2. Like alkali metals, the compounds of these elements are also predominantly ionic. If we talk about element beryllium, symbol is Be, electronic configuration is 1s2, 2s2. Magnesium, symbol Mg, configuration 1s2, 2s2, 2p6, 3s2. Calcium, symbol is Ca, configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Next is strontium, Sr is the symbol, configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 5s2. Next is barium, Ba is the symbol, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6, 6s2, or we can write xenon 6s2. Next is radium, Ra is the symbol and its electronic configuration is Rn, radon 7s2. Next topic is atomic and ionic radii. The atomic and ionic radii of the alkaline earth metals are smaller than those of the corresponding alkali metals in the same periods. This is due to the increased nuclear charge in these elements. Within the group, the atomic and ionic radii increases with increase in atomic number. Now, we have a table which represents the atomic and physical properties of the alkaline earth metals. If we talk about beryllium, its atomic number is 4. Atomic mass is 9.01. Electronic configuration helium 2s2. Ionization enthalpy 899. Ionization enthalpy 1757. Hydration enthalpy -2494. Metallic radius 111. Ionic radius 31. Melting point 1560. Boiling point 2745. Density is 1.84. Then standard potential is -1.97. Occurrence in lithosphere is 2 parts per million. Magnesium, atomic number 12, atomic mass 24.31, electronic configuration neon 3s2, ionization enthalpy 737, ionization enthalpy 1450. First is ionization enthalpy 1, second is ionization enthalpy 2. Then we have hydration enthalpy -1921, metallic radius 160, ionic radius 72, melting point is 924, boiling point is 1363, Density is 1.74. Standard potential is minus 2.36. Occurrence in lithosphere is 2.76. Calcium, atomic number 20, atomic mass 40.08, electronic configuration argon 4s2, ionization enthalpy 590, second ionization enthalpy 1145, hydration enthalpy minus 1577, metallic radius 197, ionic radius 100, melting point 1124, boiling point 1767, density 1.55, standard potential minus 2.84, occurrence in lithosphere 4.6. Next is strontium, atomic number 38, atomic mass 87.62, electronic configuration krypton 5s2, ionization enthalpy first 549, second ionization enthalpy is 1064, hydration enthalpy is minus 1443, metallic radius is 215, ionic radius 118, melting point 1062, boiling point 1655, standard potential density 2.63, standard potential minus 2.89, occurrence in lithosphere is 384. Next is barium, atomic number 56, atomic mass 137.33, electronic configuration xenon 6s2, first ionization enthalpy is 503, second ionization enthalpy is 965, hydration enthalpy is minus 1305, metallic radius is 222, and ionic radius is 135, melting point is 1002, boiling point is 2078, density is 3.59, standard potential is minus 2.92, occurrence in lithosphere is 390. Last is radium, atomic number 88, atomic mass 226.03, electronic configuration is radon 7s2, ionization enthalpy first is 509, second ionization enthalpy is 979, hydration enthalpy and metallic radius is not given, ionic radius is 148, melting point is 973, boiling point is 1973, density is 5.5, standard potential minus 2.92, and occurrence in lithosphere is 10 to the power minus 6. Next topic we have ionization enthalpy. The alkaline earth metals have low ionization enthalpy due to fairly large size of the atoms. Since the atomic size increases down the group, their ionization enthalpy decreases. The first ionization enthalpy of the alkaline earth metals are higher than those to the corresponding group 1 metals. This is due to their small size as compared to the corresponding alkali metals. It is interesting to note that the second ionization enthalpy of the alkaline earth metals are smaller than those of the corresponding alkali metals. Next topic is hydration enthalpies. Like alkali metal ions, the hydration enthalpies of alkaline earth metal ions decreases with increase in ionic size down the group. The decreasing order is given: beryllium 2 positive, then magnesium 2 positive, then calcium 2 positive, then strontium 2 positive, and at last barium 2 positive. The hydration enthalpy of the alkaline earth metal ions are larger than those of alkali metal ions. Thus, compounds of alkaline earth metals are more extensively hydrated than those of alkali metals. Example: MgCl2 and calcium chloride exist as MgCl2.6H2 and calcium chloride.6H2, while NaCl and KCl do not form such hydrates. Next topic is physical properties. The alkaline earth metals in general are silvery white, lustrous, and relatively smaller sizes. The trend is, however, not systematic because of the electropositive character increases down the group from beryllium to barium. Calcium, strontium, and barium impart characteristic brick red, crimson, and apple green colors respectively to the flame. In flame, the electrons are excited to higher energy level, and when they drop back to the ground state, energy is emitted in the form of visible light. The electrons in beryllium and magnesium are too strongly bound to get excited by flame. Hence, these elements do not impart any color to the flame. The flame test for calcium, strontium, and barium is helpful in their detection in qualitative and analysis and estimation by flame photometry. The alkaline earth metals, like those of alkali metals, have high electrical and thermal conductivities, which are typical characteristics of metal. Next topic is chemical properties. The alkaline earth metals are less reactive than the alkali metals. The reactivity of these elements increases on going down the group. First is reactivity towards air and water. Beryllium and magnesium are kinetically inert to oxygen and water because of the formation of an oxide film on their surface. However, powdered beryllium burns brilliantly on ignition in air to give BeO and Be3N2. Magnesium is more electropositive and burns with dazzling brilliance in air to give MgO and Mg3N2. Calcium and strontium and barium are readily attacked by air to form oxide and nitride. They also react with water in increasing vigor even in cold to form hydroxide. Second is reactivity towards the halogens. All the alkaline earth metals combine with halogen at elevated temperature forming their halides. M plus X2 give MX2 where halogen can be fluorine, chlorine, bromine, iodine. Thermal decomposition of NH4 whole twice BeF4 is the best route for the preparation of BeF2 and BCl2 is conventionally made from the oxide. A reaction is given where BeO plus carbon plus Cl2 at temperature 600 to 800 Kelvin gives BeCl2 plus carbon monoxide. Third is reactivity towards hydrogen. All the elements except beryllium combined with hydrogen upon heating to form their hydrides MH2. BeH2 however can be prepared by the reaction of BeCl2 with LiAlH4. A reaction is given where 2BeCl2 plus LiAlH4 gives 2BeH2 plus LiCl plus AlCl3. Next we have reactivity towards acids. The alkaline earth metals readily react with acids liberating dihydrogen. A metal plus 2HCl gives MCl2 plus H2. Next is reducing nature. Like alkali metals, the alkaline earth metals are strong reducing agents. This is indicated by large negative values of their reduction potential. However, their reducing power is less than those of their corresponding alkali metals. Beryllium has less negative value compared to other alkaline earth metals. However, its reducing nature is due to large hydration energy associated with the small size of beryllium plus 2 ions and relatively large value of the atomization enthalpy of the metal. Next is solutions in liquid ammonia. Like alkali metals, the alkaline earth metals dissolve in liquid ammonia to give deep blue-black solution forming ammoniated ions. A reaction is given M plus X plus Y in a bracket ammonia gives M NH3 bracket X2 positive plus 2 bracket E bracket NH3 Y negative. From these solutions, the ammoniates MNH3 MNH3 whole 6 2 positive can be recovered. Next is uses. Beryllium is used in the manufacture of alloys. Copper beryllium alloys are used in the preparation of high strength springs. Metallic beryllium is used for making windows of X-ray tubes. Magnesium forms alloy with aluminium, zinc, manganese and tin. Magnesium aluminium alloys being light in mass are used in aircraft construction. Magnesium powder and ribbon is used in flash powders and bulbs, incendiary bombs and signals. A suspension of magnesium hydroxide in water called milk of magnesia is used as an antacid in medicine. Magnesium carbonate is an ingredient of toothpaste. Calcium is used in the extraction of metals from oxides which are difficult to reduce with carbon. Calcium and barium metals, owing to their reactivity with oxygen and nitrogen at elevated temperature, have often been used to remove air from vacuum tubes. Radium salts are used in radiotherapy, for example, in the treatment of cancer. Next topic is general characteristics of compounds of the alkaline earth metals. The dipositive oxidation state N2 positive is the predominant valence of group 2 elements. The alkaline earth metals form compounds which are predominantly ionic but less ionic than the corresponding compounds of alkali metals. This is due to increased nuclear charge and smaller size. The oxides and other compounds of beryllium and magnesium are more covalent than those formed by the heavier and large size members calcium, strontium, barium. The general characteristic of some of the compounds of alkali earth metals are described below. First is oxides and hydroxides. The alkaline earth metal burn in oxygen to form the monoxide MO, which except for BeO have rock salt structure. The BeO is essentially covalent in nature. The enthalpies of formation of these oxides are quite high and consequently they are very stable to heat. BeO is amphoteric, while oxides of other elements are ionic in nature. All these oxides except BeO are basic in nature and react with water to form sparingly soluble hydroxides. MO plus H2O give M hydroxide, metal hydroxide. The solubility, thermal stability and basic characteristics of these hydroxides increases with increasing atomic number from magnesium hydroxide to barium hydroxide. The alkaline earth metal hydroxides are however less basic and less stable than alkali metal hydroxides. Beryllium hydroxide is amphoteric in nature as it reacts with acid and alkali both. Beryllium hydroxide plus 2OH negative gives berylate ion. Beryllium hydroxide plus 2HCl plus 2H2O gives BeOH4 and Cl2. Second is halides. Except for beryllium halides, all other halides of alkaline earth metals are ionic in nature. Beryllium halides are essentially covalent and soluble in organic solvent. Beryllium chloride has a chain structure in solid state. Next, we have in the vapor phase, beryllium chloride tends to form a chloro-bridged dimer which dissociates into linear monomer at high temperature of the order of 1200 Kelvin. The tendency to form halides hydrates gradually decreases. For example, MgCl2.8H2O, then calcium chloride.6H2O, then strontium chloride.6H2O, and then barium chloride.2H2O down the group. The dehydration of hydrated chlorides, bromide, and iodides of calcium, strontium, and barium can be achieved on heating. However, the corresponding hydrated halides of beryllium and magnesium on heating suffer hydrolysis. The fluorides are relatively less soluble than the chlorides owing to their high lattice energies. Then is salts of oxoacids. The alkaline earth metals also form salts of oxoacids. Some of these are carbonates. Carbonates of alkaline earth metals are insoluble in water and can be precipitated by addition of a sodium or ammonium carbonate solution to a solution of a soluble salt of these metals. The solubility of carbonates in water decreases as the atomic number of the metal ion increases. All the carbonates decompose in heating to give carbon dioxide and the oxide. Beryllium carbonate is unstable and can be kept only in the atmosphere of CO2. The thermal stability increases with increasing cationic size. Next is sulfates. The sulfates of alkaline earth metals are all white solids and stable to heat. BeSO4 and MgSO4 are readily soluble in water. The solubility decreases from calcium sulfate to barium sulfate. The greater hydration enthalpy of beryllium 2 positive and magnesium 2 positive ions overcome the lattice enthalpy factor and therefore their sulfates are soluble in water. Then is nitrates. The nitrates are made by dissolution of the carbonates in dilute nitric acid. Magnesium nitrate crystallizes with 6 molecules of water, whereas barium nitrate crystallizes as the anhydrous salt. This again show a decreasing tendency to form hydrates with increasing size and decreasing hydration enthalpy. All of them decompose on heating to give the oxide like lithium nitrate. A reaction is given 2M bracket NO3 bracket closed twice gives 2MO plus 4NO2 plus O2, where metal can be beryllium, magnesium, calcium, strontium or barium. Then here we are given again with a question. Question is, why does the solubility of alkaline earth metal hydroxides in water increase down the group? Answer is solution. Among alkaline earth metal hydroxide, the anion being common, the cationic radius will influence the lattice enthalpy. Since lattice enthalpy decreases much more than the hydration enthalpy with increasing ionic size, the solubility increases as we go down the group. Next question is, why does the solubility of alkaline earth metal carbonates and sulfates in water decrease down the group? Answer is, the size of anions being much large compared to cations, the lattice enthalpy will remain almost constant within a particular group. Since the hydration enthalpy decrease down the group, solubility will decrease as found for the alkaline earth metal carbonates and sulfates. Next topic is anomalous behavior of beryllium. Beryllium, the first member of group 2 metal, shows anomalous behavior as compared to magnesium and rest of the members. Further, it shows diagonal relationship to aluminum, which is discussed subsequently. Firstly, beryllium has exceptionally small atomic and ionic size and thus does not compare well with other members of the group. Because of high ionization enthalpy and small size, it forms compounds which are largely covalent and gets easily hydrolyzed. Secondly, beryllium does not exhibit coordination number more than 4, as in its valence shell there are only 4 orbitals. The remaining members of the group can have a coordination number of 6 by making use of d orbitals. Then we have Third, the oxide and hydroxide of beryllium, unlike the hydroxide of other elements in the group, are amphoteric in nature. Next topic is diagonal relationship between beryllium and aluminium. The ionic radius of beryllium is estimated to be 31 picometer. The charge by radius ratio is nearly same as that of the aluminium plus 3 ion. Here, hence beryllium resembles aluminium in some way. Some of the similarities are: firstly, like aluminium, beryllium is not readily attacked by acids because of the presence of an oxide film on the surface of metal. Secondly, beryllium hydroxide dissolves in an excess of alkali to give berylate ion BeOH4 2 negative, just as aluminium hydroxide gives aluminate ion AlOH4 negative. Third, the chlorides of both beryllium and aluminium have Cl negative bridge chloride structure in vapor phase. Both the chlorides are soluble in organic solvents and are strong Lewis acids. They are used as Friedel-Crafts catalyst. Fourthly, beryllium and aluminium ions have strong tendency to form complexes BeF4 2 negative and aluminium F6 3 negative. Next topic is some important compounds of calcium. Important compounds of calcium are calcium oxide, calcium hydroxide, calcium sulfate, calcium carbonate, and cement. These are industrially important compounds. The large-scale preparation of these compounds and their uses are described below. First is calcium oxide or quicklime, formula is CaO. It is prepared on a commercial scale by heating limestone CaCO3 in a rotary kiln at 1070 to 1270 Kelvin, where calcium carbonate on heating gives calcium oxide plus CO2. The carbon dioxide is removed as soon as it is produced to enable the reaction to proceed to completion. Calcium oxide is a white amorphous solid. It has a melting point of 2870 Kelvin. On exposure to atmosphere, it absorbs moisture and carbon dioxide. Then we have calcium oxide plus water gives calcium hydroxide. Calcium oxide plus CO2 gives calcium carbonate. The addition of limited amount of water breaks the lump of lime. This process is called slaking of lime. Quicklime slaked with soda gives solid soda lime. Being a basic oxide, it combines with acidic oxides at high temperature. Calcium oxide plus silicon oxide gives CaSiO3, whereas 6CaO calcium oxide plus P4O10 gives 2Ca3 bracket PO4 bracket close twice. Uses: it is an important primary material for manufacturing cement and is the cheapest form of alkali. Secondly, it is used in the manufacture of sodium carbonate from caustic soda. Thirdly, it is employed in the purification of sugars and in the manufacture of dyestuffs. Next is calcium hydroxide, slaked lime, calcium hydroxide, that is CaOH whole twice. Calcium hydroxide is prepared by adding water to quicklime CaO. It is a white amorphous powder. It is sparingly soluble in water. The aqueous solution is known as lime water, and a suspension of slaked lime in water is known as milk of lime. When carbon dioxide is passed through lime water, it turns milky due to the formation of calcium carbonate. CaOH whole twice plus CO2 gives calcium carbonate plus water. On passing excess of carbon dioxide, it precipitates dissolved to form calcium hydrogen carbonate. CaCO3 plus CO2 plus water gives Ca bracket start HCO3 whole twice. Milk of lime reacts with chlorine to form hypochlorite, a constituent of bleaching powder. The reaction is 2 moles of calcium hydroxide plus 2 moles of Cl2 gives CaCl2 plus Ca bracket OCl2 plus 2H2, which is bleaching powder. If we talk about its uses, it is used in the preparation of mortar, a building material. Then secondly, it is used in whitewash due to its disinfectant nature. Thirdly, it is used in glass making, in tanning industry, for the preparation of bleaching powder and for purification of sugar. Third is calcium carbonate, CaCO3. Calcium carbonate occurs in the nature in several forms like limestone, chalk, marble, etc. It can be prepared by passing carbon dioxide through slaked lime or by the addition of sodium carbonate to calcium chloride. Calcium hydroxide plus CO2 gives CaCO3 plus water. CaCl2 plus Na2CO3 gives CaCO3 plus 2NaCl. Excess of carbon dioxide should be avoided since this leads to the formation of water-soluble calcium hydrogen carbonate. Calcium carbonate is a white fluffy powder. It is almost insoluble in water. When heated to 1200 Kelvin, it decomposes to evolve carbon dioxide. CaCO3 at 1200 Kelvin gives CaO plus CO2. It reacts with dilute acid to liberate carbon dioxide. CaCO3 plus 2HCl gives CaCl2 plus H2O plus CO2. Next reaction is CaCO3 plus H2SO4 gives CaSO4 plus water plus CO2. Uses: it is used as a building material in the form of marble and in the manufacture of quicklime. Calcium carbonate along with magnesium carbonate is used as a flux in the extraction of metals such as iron. Specially precipitated CaCO3 is extensively used in the manufacture of high quality paper. It is also used as an antacid, mild abrasive in toothpaste, a constituent of chewing gum, and in filler in cosmetics. Next is calcium sulfate plaster of Paris. Calcium sulfate CaSO4 dot half H2O. It is hemihydrate of calcium sulfate. It is obtained when gypsum CaSO4.2H2 is heated to 393 Kelvin. A reaction: 2 moles of CaSO4.2H2O gives 2 moles of calcium sulfate.H2O plus 3 water molecules. Above 393 Kelvin, no water of crystallization is left and anhydrous calcium sulfate CaSO4 is formed. This is known as dead burnt plaster. Next, it has a remarkable property of setting with water. On mixing with an adequate quantity of water, it forms a plastic mass that gets into the hard solid in 5 to 15 minutes. Uses: the largest use of plaster of Paris is in the building industry as well as plasters. It is used for immobilizing the affected part of an organ where there is a bone fracture or a sprain. It is also employed in dentistry, in ornamental work, and for making cast of statues and bust. Next is cement. Cement is an important building material. It was first introduced in England in 1824 by Joseph S. Fidden. It is also called Portland cement because it resembles with the natural limestone quarried in the Isle of Portland, England. Cement is a product obtained by combining a material rich in lime, calcium oxide with other materials such as clay, which contains silica, SiO2, along with the oxides of aluminium, iron, and magnesium. The average composition of Portland cement is calcium oxide 50 to 60%, silicon oxide 20 to 25%, aluminium oxide 5 to 10%, magnesium oxide 2 to 3%, iron oxide 1 to 2%, and SO3 1 to 2%. For a good quality cement, the ratio of silica SiO2 to alumina Al2O3 should be between 2.5 and 4, and the ratio of lime calcium oxide to the total of the oxides of silicon, aluminium, and iron should be close as possible as to 2. The raw materials for the manufacture of the cement are limestones and clay. When clay and lime are strongly heated together, they fuse and react to form cement clinker. The clinker is mixed with 2 to 3% by weight of gypsum CaSO4.2H2 to form cement. Thus, important ingredients present in Portland cement are dicalcium silicate Ca2SiO4 26%, tricalcium silicate Ca3SiO5 51%, and tricalcium aluminate Ca3Al2O6 11%. Next topic is setting of cement. When mixed with water, the setting of cement takes place to give a hard mass. This is due to the hydration of the molecule of the constituents and their rearrangement. The purpose of adding gypsum is only to slow down the process of setting the cement so that it gets sufficiently hardened. Next is uses. Cement has become a commodity of national necessity for any country next to iron and steel. It is used in concrete and reinforced concrete, in plastering, and in construction of bridges, dams, and buildings. Biological importance of magnesium and calcium. Next topic. An adult body contains about 25 gram of magnesium and 1200 gram of calcium compared with only 5 gram of iron and 0.06 gram of copper. The daily requirement in the human body has been estimated to be 200 to 300 mg. All enzymes that utilize ATP in phosphate transfer require magnesium as the cofactor. The main pigment for the absorption of light in plants is chlorophyll, which contains magnesium. About 99% of the body calcium is present in bones and teeth. It also plays important role in neuromuscular function, interneuronal transmission, cell membrane integrity, and blood coagulation. The calcium concentration in the plasma is regulated at about 100 mg per liter. It is maintained by two hormones, calcitonin and parathyroid hormone. Do you know that bone is an inert and unchanging substance but is continuously being solubilized and redeposited to the extent of 400 mg per day in a man. All this calcium passes through the plasma. So this was the whole chapter, the S block.